In the previous video, we have discussed about the half-wave rectifier. In this video, we'll discuss about the full-wave rectifier. Already I have told you the full-wave rectifier converts both positive half cycle and negative half cycle of the AC into the direct current. Okay, so in full-wave rectification, the current flows through the load in the same direction for both the half cycles, that is positive and negative half cycles. This can be achieved by using two or more diodes working alternatively. That means when one diode is forward biased, then another diode may be reverse biased. And in the other case, the second diode may be forward biased with first diode with the reverse biasing condition. So at any time, one of the diode or one or more diodes will be forward biased so that the both positive and negative half cycles will be converted into DC. So there are two types of full wave rectifiers based on the connection type. One is center tap full wave rectifier, another one is the full wave bridge rectifier. We'll discuss both of them one after the other. So this circuit shows the center tap full wave rectifier. So here the input AC is given to the transformer and the load resistance is connected to center of the transformer. That is the reason why it is called center tapped. That means this transformer consists of three terminals, the top point A, the middle terminal, that is the center tap terminal O, and the bottom terminal B. So that the input voltage will be divided into two parts, one part across OA, another part across OB. Suppose input AC is 50 volt, the 25 volt will appear across this OA and the remaining 25 volt will appear across OB, so that at the center a wire is taken out and it will capable of dividing the input voltage into two equal parts. Okay, so in this circuit, two diodes are used, diode D1 and diode D2 connected in this manner. Okay, how it works? Basically, when the positive half cycle is fed to the input circuit, then the point A becomes positive and point B becomes negative. Okay, point A becomes positive and point B becomes negative. So when positive terminal is connected to P region of diode D1, then D1 becomes forward biased and current will pass through the diode D1. At the same time, when negative terminal is connected to the diode D2, then it will become reverse biased. No current will flow through the diode. That means during the positive half cycle, diode D1 will conduct the current and diode D2 will not conduct the current. That means the current will flow through D1 and that will flow through the load resistance in this direction, that is from right to left. This arrow mark shows the direction of the current during the positive half cycle. Okay, that is the dotted arrow marks. On the other hand, when a negative half cycle is fed to the input circuit, then the point A of the transformer becomes negative and point B becomes positive. Then what happens? Diode D2 will become forward biased and diode D1 will become reverse biased. Okay, because of that, diode D2 will pass the current, whereas D1 will not pass the current. So that means the current will flow through the D2 and this solid arrow mark shows the direction of the current. If you observe the current direction through the load resistance, that is again from right to left. So during the positive half cycle also, the current direction is right to left. During the negative half cycle also, the current direction is right to left. So through the load, the current direction is same. So in this direction, the current will flow. That is shown according to the arrow mark. Whatever may be the direction of the input current, the direction of the output current through RL will be in same direction. That is in unidirectional. That is called as DC. So even though the AC is supplied to the circuit, the output taken across the RL will be the direct current. So this will be the nature of the output voltage. So here during the positive half cycle, D1 is conducting. Because of that, the output half cycle is observed here in this positive direction. During the negative half cycle of the input, the diode D2 will conduct, and because of that, this half cycle is obtained. Again, that is in same direction. Similarly, the positive half cycle, negative half cycle. So this D1, D2, D1, D2, alternatively, they will conduct the current and output will be continuous with both both positive cycles. Okay. So current in the load is in the same direction during the positive and negative half cycle of the AC input. So this is how the full wave rectifier works. The name is full wave rectifier for this circuit because it will convert the full wave, that is entire wave, both positive and negative half waves into the DC. That's why it is called as full wave rectifier. And this is the circuit of center tap full wave rectifier. Let us take the full wave bridge rectifier. And here in this bridge rectifier, 4 diodes are used and they are connected in this quadrilateral form. Okay. So as in rectifier circuit, the input is AC and here center tap is not used. Instead of center tap, the normal transformer is used where the one point is called as point P, another end is called as point Q. So here diode D1, D2, D3 and D4 are connected in this manner, in this quadrilateral manner. And this point A is connected to ground and this point B is connected to load resistance and output is taken across the load resistance. Okay. So this is the input voltage, that is positive and negative half cycles. Okay. This is fed to the circuit. Then the output will be the full wave output. That is both the positive and negative half cycles will be converted into the direct current. So how it works? So that can be understood by taking the working of this full wave bridge rectifier during the positive half cycle and negative half cycle. Let us consider this circuit and what happens to this circuit during the positive half cycle. So this is the circuit showing the positive half cycle. So when AC input is positive half cycle, then point P becomes positive and point Q becomes negative. Okay. So when P becomes positive, then this positive terminal is connected to P region of diode D1, whereas it is connected to N region of diode D4. So that current will pass through D1, whereas there is no current through the D4 because D4 is reverse biased. Okay. Similarly, when it comes here, this diode D3 will become forward biased. So what happens during the positive half cycle, diode D1 and D3 become forward biased and they will conduct the current so that the current will flow through like this. It will go to the ground and from the ground, it will go through this D3 and it will reach the point Q. The current will flow from point P to D1 and it will go to ground, and from ground it will flow through the resistance RL and it will flow through the diode D3 and it will reach the point Q of the transformer. This is the direction of current during the positive half cycle. What is the direction of current through this load resistance? This is from bottom to top in the upward direction, so that the direction of current is in the upward direction during the positive half cycle. Then what will be the current direction through this load during the negative half cycle? So this is the structure. So during the negative half cycle, this point P becomes negative and point Q becomes positive. So this shows the direction of current. The current will flow from the positive terminal of the transformer, then diode D2 and D4 becomes forward biased and D1 and D3 become reverse biased. So current direction is shown using this arrow mark. It will flow from point Q to D2 and it will go to ground, and from the ground it will flow through the resistance RL and it will flow through the diode D4 and it will reach the point P. So again you observe the direction of current through the load is from bottom to top in the upward direction. During the positive half cycle also, the direction of current is in the upward direction. During the negative half cycle also, it will be in upward direction. So in case of full wave bridge rectifier, during the positive half cycle, D1 and D3 will conduct the current. During the negative half cycle, D2 and D4 will conduct the current. So that is the reason why alternatively D1, D3 and D2, D4 will conduct the current during the positive half cycle and negative half cycle respectively. And the direction of current through the load will be in the same direction. That is actually the bidirectional current will be converted into unidirectional current through the load. Suppose if you calculate the efficiency of full wave rectifier, that is center tap as well as the bridge rectifier. So that will have the same efficiency, or expression for efficiency will be same. So let us consider the input voltage is Vm sin theta, where Vm is the peak voltage and Rf is the resistance of the diode and RL is the resistance connected at the load. Okay. Then for full wave rectifier, what is the output current and input current you can specify, and the output power and input power you can calculate. The efficiency of the rectifier, it is defined as the ratio of output power to input power. So what is the average DC current output? That will be 2 times Im divided by pi. Why the factor 2 is coming here? Because both the cycles are converted into DC. It is full wave rectifier. That is the reason why the output DC current will be 2 times Im divided by pi. Similarly, the AC input current is given by Im divided by root 2. That is the RMS value of the AC. So always RMS value of the current is given by peak current Im divided by root 2. For half wave rectifier, it will be Im by 2. For full wave rectifier, this RMS current is Im divided by root 2. Now you calculate the input power and output power, where electrical power is given by current square into resistance. Okay. Now DC output power is given by PDC is equal to DC current square into load resistance RL. So what is the DC current here? It is 2 Im by pi. Similarly, the AC input power is given by IRMS square into RF plus RL, where RF is the diode resistance, RL is the load resistance. Now you take the ratio of output power divided by input power. That will give you the efficiency of the full wave rectifier. So efficiency of full wave rectifier is given by PDC divided by PAC. So that is equal to IDC square into RL, that is the output DC power, divided by IRMS square into RF plus RL, that is the input AC power. Take this ratio, substitute for IDC, that is 2 Im divided by pi, substitute for IRMS, that is Im by root, the whole square. Okay. Then Im gets cancelled. This numerator will be 4 divided by pi square, and here root 2 square means 2. So you will get 8 divided by pi square into RL divided by RF plus RL. That is the expression for the efficiency of full wave rectifier. Okay. Suppose you take the maximum efficiency, if you try to calculate, then eta can be given by this expression, just we have derived in the previous slide. Now divide this expression by the load resistance RL. Divide numerator by RL and denominator by RL. So this numerator will become RL by RL, that will be equal to 1. The denominator will be RF by RL plus 1. Okay, this becomes RL by RL, this becomes 1. Now this diode resistance is very much small compared to the load resistance. Therefore, this RF by RL can be taken as very, very less than 1, or it is negligible. So you can neglect this particular ratio because of the small resistance of diode. Then the maximum efficiency is observed. So what is the maximum efficiency? That is going to be simply 8 divided by pi square for full wave rectifier. If you calculate this ratio, that will be 0.81. If you take the percentage efficiency, that will be 81%. That is obtained by just multiplying this factor by 100. So this shows that the full wave rectifier is having maximum efficiency of 81%. Okay, so that 81% of the AC power can be converted into DC power. So this is observed that the efficiency of full wave rectifier is double of that half wave rectifier. We have observed that for half wave rectifier, the efficiency is 40.5%, only 40%. But for full wave rectifier, the efficiency is 81% because it converts both the cycle of AC into DC. Okay, so in the next video, we'll take up the derivation of ripple factor for both half wave rectifier and full wave rectifier.